or the NORFMA Idaho Technical Committee, you can go to the websites. Idaho AWRA has a website. If you, I think we can share the link for that. And then NORFMA has a website as well. I'll put both of those in the chat box during the presentation. And with that, I'll turn it over to Hannah to kick off her presentation. Hannah, thanks again, and here you go.
The Bureau of Reclamation and also the Hazards and Climate Resilience Institute of Boise State University, which is led by Dr. Brittany Brand. And the title of my talk today is Modeling the Teton Dam Failure for Downstream Consequences and Validating the GeoClaw Code with Geophysical Techniques. This research is conducted with an NSF award from the DMS 1419108, and this was awarded to my research mentor, Dr. Donna Calhoun. I would like to thank the Idaho section of the American Water Resources Association, or the IDAWRA, and the Idaho Technical Committee of the Northwest Regional Floodplain Management Association for hosting this talk and giving me a platform to share my research. And I would also like to thank the National Association of NORFMA, which is the Association of State Floodplain Managers. And this past month, I was able to present the student paper process, which was, I submitted an abstract and they judged us. Then I wrote a paper and then presented at their national conference. And based on those three, they awarded first, second, and third place in the order you see on the picture. And I'd like to thank Dr. Brittany Brand at Boise State as she sent out this opportunity in January to the department. So without her, I wouldn't have even known about it. And I'd also like to thank ASFPM for their wonderful virtual conference experience. The talk today will be similar, but more in depth, pun intended, to the ASFPM talk. For an overview, I will introduce myself, I will define acronyms and terms, and I will walk you through my motivations to conduct this research. I will then introduce you to my big picture research questions and research objectives. Then I will guide you through the two phases of my methods, introducing the main tool I'm using to conduct this research called GeoClaw. Then I will present my results, a discussion, and touch on outreach opportunities that are within the broader research impacts of this research. So to begin with a little bit about me, I began my collegiate career as a student athlete at Central Washington University in Ellensburg, Washington. And it was there where I took my first Geosciences course from Nick Zentner. And I was excited that the Earth had a story to tell and geologists were here to interpret it. I was hooked, and I had had no intention previously of being a Geosciences major. So this was pretty exciting. And the following summer on the left, I took CWU's field camp in Bishop, California, and that solidified for me that I wanted to major in geosciences. The professor of that course, Bree, became my first research advisor, and I worked under her modeling tsunamis within the Puget Sound of Washington using this software called GeoClaw in the building on the right. At the beginning of my junior year, following 2 years of playing college softball, I shattered my foot in the fall season, and I became a medically retired college athlete. And I had limited mobility, and accessibility on campus was not ideal. And therefore, as an Idaho native, I moved back home to Boise. It was then I decided to attend Boise State University for my final 2 years and major in their geosciences program. As a junior at Boise State, I've conducted undergraduate research under Dr. David Wilkins, studying viticulture and soils. And I've also conducted research studying wildfires and their aerosol effects on urban environments with the University of Washington. And now I've progressed into more of my area, as I like to think of it, which is computer simulations combined with geology research. And I'm working with Dr. Donna Calhoun studying the Teton Dam failure. And if he's here, I'd like to shout out Dr. Alex Witzel for putting me in contact with Dr. Donna Calhoun. And I'm excited to share this research with you. I wanted to go over some acronyms I might use throughout this talk and a definition or two. So to begin with, ASFPM is the National Association of State Floodplain Managers. The HCRI is the Hazards and Climate Resilience Institute of Boise State University. The ASDO is the Association of State Dam Safety. The USACE is the United States Army Corps of Engineers. And when defining downstream consequences, I'm focusing on the flood result following the dam failure. So that's inundation, boundaries, velocity. And in the case of the Teton Dam, we're specifically looking at downstream consequences using the valley storage downstream of the dam and how it affects flood wave attenuation. Another term I will use throughout this talk is software validation, which is the comparison of my model results from the simulation to direct measurements historically. And without further ado, let's move into my motivations. So dam safety hazards are prevalent worldwide, and millions of lives are at risk if dams were to fail. So on the right, you can see there's a graphic, and every red dot is a dam within the United States. And this is from the ASCO. And this communicates how large a threat dam failure is in the United States. But of those dams, there is another image which depicts dam failures across the United States. And the key for this image is on the left. The colors indicate the year the dam in question failed, and the Teton Dam is in yellow as it failed in 1976. The size of the circle illustrates how many fatalities the failure produced. As you can see, the Teton Dam failure is the second largest circle, as 11 people died as a result. Another motivation for my research stemmed from my tsunami research I had done previously. I had numerically modeled tsunamis in the Puget Sound of Washington, which is on the coast. And I knew this was a low cost and flexible approach to hazard mitigation. And on the right, you can see a GIF of overlaid time snapshots of the Tohoku 2011 tsunami, which was modeled with GeoClaw by the University of Washington, Dr. Randy Levesque and Frank Gonzalez. And so having done this research previously, I thought, well, why wouldn't it be able to be adapted to dam failure, where we should be using every tool possible that we have to improve our knowledge and understanding. The final motivation behind my research was improving community resilience and preparation in case a dam failure were to occur. So I'm going to pull up my chat box here, and I'd like to show the little animated hands. How many of you have heard of the Edenville Dam? You likely heard of it on May 20th of this year. That's your small hint. Okay, I see a couple people. So this dam failure occurred in Michigan. You likely heard of the two dams that failed in Michigan. So on the right, there's the Edenville Dam, and then several dams failed. So the Edenville Dam failed first from heavy rainfall, and its infrastructure was already deteriorating. And then from that failure, the Stanford Dam failed next. So this is a modern example of where residents were evacuated, but their livelihoods and communities were utterly devastated. And so I view the Michigan dam failures as a warning about dam infrastructure around the nation and how it's deteriorating as dams get older. And the Michigan dams are another part of the cascading dam failures that have been occurring. And so I view it as we need to use all tools necessary to improve our understanding of dam failure, because it's not about if dams are going to fail, but when, and how prepared can communities be when they do. And with the focus on Idaho, I wanted to walk through a couple of the oldest dams in Idaho and talk about them. So first, the Arrowrock Dam opened in 1915, and it was built to provide irrigation water for agriculture in the area. And at 350 feet tall, it was the tallest dam in the world for 9 years, according to the Bureau of Reclamation. There's a fun fact. And so it's about 105 years old. So slightly off topic, but since we have developed our skill of using the little hand, how many of you guys have heard or watched the Today Show? Nice. Okay, I see 3 participants raised your hands. That's a small number, but that's okay. Either way, on the Today Show, when I was little, my grandpa was almost 100 years old, and it was our family's goal to put him on one of the Smucker jars that celebrates individuals who are 100 years old or older. So I felt, for comparison and perspective, I'm going to show a jar that's the same age as the Ararup Dam. So if this dam was a person, it would be Lee James of Texas. He lived to 106 years old in 2016, and he was 1 year old when that dam opened. The next dam I'm going to talk about is the Minidoka Dam. It opened in 1906. It was 86 feet tall, but it's one of the oldest dams in Idaho at 114 years old. So if this dam was a person, it would be Gertrude Weaver of Arkansas. She lived to 114 in 2013, and she was born in 1898. So she was 8 years old when this dam was constructed. And finally, there is the Swan Falls Dam, which opened in 1901, and it's 119 years old. And unfortunately, there's no Smucker jars for comparison here because this dam is that old. So this gives you perspective on the age of our dams in comparison to humans. So some of the driving big picture research questions I'm working to answer with Dr. Donna Calhoun are, what are the major sources of uncertainty in this model? How important is it to integrate a variable surface roughness as opposed to a uniform Manning's N? How accurately do we need to model the initial dam failure to represent the historical data? How can we incorporate historical data for validation purposes? And a question I'm focusing on as an interdisciplinary student researcher is what combination of applied mathematics, civil, and geosciences will allow for the best modeling of flood geohazards? And you will notice for a portion of this talk, we will focus on geoscience. And for another portion of this talk, we will focus on applied mathematics. And so mentally prepare yourself for either, depending on who you are, if you're a civil engineer or in academia for geosciences. When setting out to model the Teton Dam failure, I set several research objectives in order to answer the driving research questions we just talked about. So first, I wanted to use the 2D shallow water wave equations to model the Teton Dam failure with an evolving free boundary and free surface embedded into a background Cartesian mesh. Second, I wanted to run a high resolution simulation using dynamically evolving meshes to model the flood for the full flood duration, which, in case you're wondering, the dam failed at 11:55 a.m. on a Saturday, and it ran for a full 24 hours until it hit the American Falls Dam. And third, for model validation, we use numerical gauges for easy comparison between historical data and the model output. And this is how I aim to answer research question number 2. Fourth, it was critical to model the historic reservoir volume accurately, as it strongly influences peak elevations of flow at downstream points. And another goal was to accurately model the initial dam break. And finally, my last research objective was to combine geophysical and geological methods with numerical modeling to ensure model validity. Now that you know my motivations, I will now walk you through background information regarding the Teton Dam failure. So imagine you're in Eastern Idaho and it's 1976, it's June 5th and it's a Saturday, and you're on a farm town hanging out with friends. However, upstream there is chaos as the Teton Dam is beginning to breach. It's only been fully filled a week, but the process of filling the dam was supposed to take a full year. And so the manager on site sends 3 bulldozers, which are too small to be seen, to patch the spurting hole with gravel. However, at 11:20 a.m., the leak is widening into a flow, and 2 of the bulldozers are swept downstream, and the third barely outruns the spreading breach within the dam. 10 minutes later, it's 11:30 a.m. and the dam is pouring water. And this is when they call media to the scene. And if you look into background research on the Teton Dam, you'll hear radio stations broadcasting, "You should get your material and get out." So imagine you get the radio broadcast while you're hanging out with your friends and you immediately leave to go to high ground. At 11:55 a.m., the dam crest breaches and the Teton Dam fails. So before the failure, the Teton Dam looked like the image on the right. However, the dam failure resulted in the deaths of 11 people, 6 of those people drowned. Cattle heads were lost. The total damage in today's dollar ranged from $2 to $2.5 billion to those who were impacted. So this was a significant dam failure. The Teton Dam had a height of 305 feet. It released the volume of 250,000 acre feet, and it resulted in the deaths of 11 people. So information like this I used to parameterize my model so it would accurately reflect the historical data. Now, when I say the historic Teton Dam was 305 feet tall, that might not mean a lot without perspective. I could say I'm 5 feet 5 inches tall, so the dam would be about 56 Hannahs tall. But that's slightly silly, and also you can't see me in person, so you don't have that perspective. So instead, let's use buildings. If you've been to Boise in Idaho before, you'll know 8th and Zion's Bank on the left. It usually has a large Christmas tree in December. And on the right is the Idaho State Capitol building. So comparing Zion's Bank for scale, which is 325 feet tall, it'll only be 20 feet taller than the historic dam. So that's how massive this dam is. And on the other hand, the Idaho State Capitol is about 208 feet tall. So it'd be 2/3 the height of the Teton Dam. So the Teton Dam actually was the largest dam that ever failed in the United States, according to ASCO. So this is a substantial modeling project with a lot of complexities. There are two specific studies that I would like to acknowledge in chronological order that also have modeled the Teton Dam failure. So first, in 1977, the Bureau of Reclamation used a preliminary version of HEC-RAS to model the Teton Dam failure. Some of the parameters they instituted were instantaneous flood development rather than gradual, and the break was an approximated breach for the development. They used 1D models for historical water to transverse the flow because a 2D model wasn't feasible. And you may be wondering, well, why is that picture on the right so small? Well, if I blow it up, it gets equally as blurry, unfortunately. So I would advise you to go look at the report if you're interested. I have the link in the upper right-hand corner. And this is one of their outputs, which is the computed water surface elevation throughout the floodplain. And this HEC-RAS model was the first of its kind, so it had substantial model input and processing times like 7 weeks. And on the right is an image of the first publicly available version. And this was about 20 years later that the publicly available version came out. And this HEC-RAS model used the Savant equations for free surface hydraulic modeling, which is what the majority of dam failure softwares use today based off of this approach. And it integrated the volume of water in the reservoir historically for accuracy. And then as a full disclaimer, I have never used HEC-RAS before. I'm planning on learning it later this summer and then this fall in my hydrology course. But if you have any pointers on how this HEC-RAS study could be integrated differently into my research, I welcome that. The second study I'll give you an overview of involved modeling the Teton Dam in a coupled flow approach. And this was a collaboration between the Idaho National Laboratories and Boise State University and a company in LA called Neutrino Dynamics, Inc. This study focused on an exaggerated Teton Dam failure, and it modeled those flood waves inundating a fictitious nuclear power plant. This work in 2015, using this approach, modeled the GeoClaw Dam failure, took that output, and then plugged it in as the inflow into the 3D domain of the neutrino flow model, which you can see at the right, which models individual particles. I will now introduce to you the software I'm using as a tool to look at dam failure and downstream wave propagation. So to begin with, the Clawpack software is based on the Clawpack conservation laws, which were originally developed in 1994. And since there has been continuous development, it models wave propagation by solving a system of hyperbolic partial differential equations. And in 2004, GeoClaw was created. Some features of the software are, in general, it solves 2D shallow water wave equations over topography. In addition, it handles shoreline or the edge of the flow by allowing some cells to be dry and some cells to be wet, and they're dry when the water depth is 0. and it handles these through a dynamically changing interface. Another big component of GeoClaw is it uses adaptive mesh refinement, which is in a block structure manner within an adaptive grid, and it uses shot capturing finite volume methods that have been developed over the past 30 years. So it effectively captures flow even if there's discontinuities like hydraulic jumps. And I will show you an example in the next couple of slides. Although GeoClaw does not have massive parallelism like its sister software ForestClaw, which Dr. Donna Calhoun created, it does work with OpenMP on shared memory machines, and it's accessible through a Python interface. So it can work to have extremely fast computations and be quite efficient. All of the development of GeoClaw is logged on GitHub, so using the link above, you can see the information on this software if you're interested. And I'd also like to acknowledge core developers. Dr. Randy Levesque was the core creator originally. Dr. Marcia Berger developed the adaptive refinement portions of GeoClaw. Dr. David Ketchinson contributed a lot to initial development. Dr. Kyle Manley developed storm surge modeling. And Dr. David George developed Tsunami Claw, which turned into GeoClaw, and he also developed DClaw. And then my research mentor, Dr. Donna Calhoun, developed ForestClaw. And at the bottom are some of the funding sources for Clawpack. So GeoClaw is one of the several softwares that falls under Clawpack, and some sister softwares are DClaw, which models debris flows, BoostClaw, which models dispersive wave tsunamis, like landslide triggered tsunamis, and ForestClaw provides a high performance version of all Clawpack applications. And it's been validated for tsunami modeling, Hortonian overland flooding, and storm surges. And now we are using it for dam failure. This might be review for some of you who have finished school, but GeoClaw is specific to the 2D full shallow water wave equations, which you can see in the middle. So in these equations, U and V are the velocities in the horizontal directions, and there are incorporated depth average velocities. The 1/2 GH squared term in the middle, you can see this is the hydrostatic pressure term, and then the capital B on the right is the topography that the flow is going over. So for example, if B is negative, then it's underwater, and if it's positive, then it's going to be dry. So applying this equation into a dam break example, the red stripes of water are a wall of water, and the colors are all water in this example. This is an example of a wave propagating to the right-hand side. And so the blue is just a lower level of water. So it's a passive tracker. The first equation you can see has constant velocity. So this would just shift the red block of lines to the right. However, the second equations is the red block of water, we can consider it like a wall of water, and it has a mass. So that mass times acceleration will create momentum, and that affects the pressure terms. So that therefore will transfer the water across the vertical faces. So here we can see on the left-hand side, there's the wall of water rarefaction wave, which is moving back as the stripes get closer together. And then as the stripes get squished in the front, this is where there's a hydraulic jump developing on the right-hand side. And so this example uses row approximate solvers, and the Riemann solver robustly handles wet dry states. So this is an example of the dam break problem. And then this is a 1D example. So a 2D example is here, and this is a simulation of the shallow water model, which is built into a rectangular Cartesian grid, where each cell of the grid has variables like water level, momentum in the X and Y direction, and the topography of the data instituted is uniform. So this is showing multiple time steps computed with ForestClaw as they solve and compute for SWE. I like to think it reminds me of a kaleidoscope. So phase 1 of my research consisted of modeling the Teton Dam failure using adaptive mesh refinement to define subgrading techniques, and it adapts in time, which a lot of codes do not do. It also involved resolving local inundation and the evolving wet-dry front, which is in the front here outlined in yellow. And this is one of my simulation runs depicted over Google Earth topography. Next, I inserted numerical gauges into the simulation. On the left-hand side of this table in the darker color, these are the model values such as the location and the number for each gauge. And then on the right-hand side in the light gray color, these are the Bureau of Reclamation historical values at the location of each gauge that I'm working to collaborate with within the GeoClaw model. So flooding depth, flood arrival time, and miles from the dam. And also in phase 1, I focused on maximizing computational efficiency by using the Boise State University Supercompute Cluster, R2. And so for those of you who are interested or computer nerds, each model run takes between 3 to 4 hours rather than the full 24 it would take on my laptop. And I run on 4 nodes, each of which has 28 cores. And finally, in phase 1 of my methods, I use Google Earth instead of field work due to COVID-19 to model the volume of our simulation and compare it to historical volume. I used Google Earth in the yellow lines you can see at the right depicting polygons, and I took cross sections every half a mile for the 17-mile reservoir. And I then determined the value for the hypotenuse. There, I averaged all the hypotenuses, and I used the equation for a triangular prism flipped upside down to calculate the average model volume. The average model volume was 284,750 acre feet, and this compared well to the historical value of 288,250 acre feet. So without verification, I moved forward in my modeling. Phase 2, I plan to conduct this fall, and it depends on restrictions for fieldwork, of course, but I plan to use drone photogrammetry and structure from motion, or SFM. And if you haven't heard of these before, SFM can be defined as like a photogrammetry, as drone photogrammetry, which has a range of imaging techniques. So I would use a drone to fly over topography, similar to the image on the right, and they would stitch together 2D images into a 3-dimensional structure called a point cloud structure. And from there, I could implement this as a digital elevation model into my simulation. So with SFM, I would have the ability to characterize the initial failure of the Teton Dam better. I would also have the ability to increase the resolution through using the digital surface model. And so currently my topography files are 10-meter resolution, which is fairly good. However, with these techniques, I could improve the resolution of the dam up to 1 meter. And so also with this structure for motion campaign, I would be able to produce outreach animation modeling, which is a broader impact of this research. So to improve the modern topography, we can see on here, there's 2 different images. There's a cross-section image from Google Earth and a map view with the flood simulation on top that has not yet been released. And you can see there's wide blue pixels and they don't fully fit to the line of the reservoir. However, they fit well to the first degree. So by doing a high resolution campaign in this area, we would be able to fit this model extremely well, which I would hypothesize would improve our model drastically. Additionally, as you can see in these images, there is a flat wall of water that is waiting to be released. So like the HEC-RAS model of 1977, we made the assumption that the dam breach developed instantaneously and completely. As the storage area elevation drops to the topographic elevation, that's when the floodwaters are released. So if we had a higher resolution of the initial dam, we would be able to implement smaller variable steps and we could potentially do a gradual dam failure, which is one of the goals we are working towards. Another goal of this approach is to integrate HRT, or high resolution topography, into GeoClaw, which has not been done before. In the bottom 2 images from Dr. John Swartz of UT Austin, you can see the difference that high resolution topography can make. An additional aspect of this research would be phase 2 of my methods could provide a different workflow for industry professionals where there might be low resolution topography as the only option, as their LiDAR campaigns can be quite expensive. But you could use a field campaign for drone photogrammetry to gather low cost drone images, and this could be a perfect substitute. So that's another aspect of my research. The final goal of phase 2 would be to institute a variable Manning's roughness into the simulation, which also has not happened as of yet. The historical HEC-RAS simulation used the same Manning's N that we're currently using of 0.025. However, using a uniform surface value doesn't produce as accurate a model, I would hypothesize, as a variable Manning's N would. And here I will give you an example of why I'm integrating surface roughness. So first, if you've taken a hydrology class, you likely learned the fluid velocity equation at the right. I plugged in all the same values except for the N values for this example. I plugged in the coefficient for concrete, for rangeland, and for low intensity developed urban areas. And what I found out when plugging in these values is they're vastly different. So concrete is much larger than rangeland, and rangeland is still less than developed low intensity urban environments. And all three of these were present within the flow boundary for the Teton Dam failure. So I think it's instrumental that we implement a Manning's roughness coefficient. With those methods, I've progressed through phase 1 of modeling the Teton Dam failure, and I will show you my results over the next few slides. I will be showing you Teton Mouth gauge, the Wilford gauge, the Sugar City gauge, and the Rexburg gauge. Additionally, when you're looking at the GeoClaw simulations overlaying Google Earth, the boundaries of the historic flood you can see outlined here in red, and this follows the Historic Bureau of Reclamation outline of the flood, which is on the left. And I also show you Rexburg on both of the maps for reference. Additionally, you will see a color bar in the bottom left-hand corner of many of the simulations. This shows the inundation on Google Earth from 0 to 5 meter resolution. And with the floodwater depth being above 5 meters, it would just be ranked in the dark blue color still. So to begin with, the Teton Dam mouth gauge shows flood waves over 30 feet high and immediate flood inundation occurring at noon or 12 p.m. This gauge demonstrated historical agreement with waves close to 40 feet in depth as the flow broke out of the canyon at 12:10 p.m. So moving downstream, the next gauge downstream is the Wilford gauge. Historically, the flood arrived here at 12:45 p.m. with inundation depths of 15 feet. In the GeoClaw simulation, the gauge largely agreed with the historical data as it displayed a depth of 15 feet. The model shows the floodwaters arriving at the town at 1 p.m., which agrees with the 12:45 arrival time, although it's slightly later. The Sugar City gauge showed that floodwaters arrive at 1:20 p.m., which is in general agreement to the historical literature value of 1:30 p.m. arrival time. The depth as displayed in the gauge is around 10 feet, which is close to the value of 15 feet, although slightly lower. And finally, the Rexburg gauge also demonstrated inundation agreement with a model value of 6 feet as opposed to the historical depths of 6 to 8 feet, which vary per area where the Rexburg gauge would be inserted. The model refinement begins at 1:15 p.m., which is shown on the left in the green color. This is the topography, and it's the one that looks like the cactus shape, but when it begins the flat line, that's when the model begins to register the flood occurring. And it's also interesting to interpret the gauge on the left, where in my opinion, there seems to be a second wave hitting Rexburg or a rarefaction wave moving backwards towards Wilford around 7 p.m. And I will discuss this further in the discussion section, so keep it in mind. So here you can see the progression from the top left corner to the bottom right-hand corner of the flood being modeled. The town of Teton and Roberts are gauges that Dr. Donna Calhoun inserted, so those are her images, but the other 4 are mine. And you can see here the progression, and it falls within the flood boundary line, which is one of the calibrations we were looking for. And this also follows narrative descriptions that are available on open source. So for instance, in the Roberts image in the bottom right-hand corner, it's flooding around Min and Butte. And therefore we can see that it's registering the topography. Largely across all 7 gauges, the inundation levels matched historical records of geographic spread. And this is a compelling indicator that GeoClaw can be adapted for dam simulations. Additionally, its high water marks showed good agreement with the historical boundaries showed at the time of the Teton Dam flood in historical imagery. So that's another strong, compelling argument. And using the Wilford gauge as an example, floodwaters here reached the gauge within 15 minutes of the historical literature value. So within the numerical fidelity of the model, we considered this to be excellent agreement. We looked for plus or minus 15 minutes. With application of phase 2, I expect that the high resolution of the dam will improve arrival times, inundation depths, and geographic spread, which should improve the simulation overall and therefore could validate the GeoClaw software and for Teton Dam for that failure specifically, but also potentially for futuristic modeling. With the validation, we could conduct the futuristic modeling for flood maps for local communities, communicate threats to lawmakers in visually impactful ways, and potentially aid in the design and location of future dams. And 3 ways I specifically see that GeoClaw could be integrated besides just inundation modeling would be for risk management, evaluation, to estimate the economic consequences within dam failure scenarios to the 1st degree, and to estimate loss of life in general. And this all, of course, has to be done with potentially improved funding from the United States Congress to the Bureau of Reclamation and the US ACE. So they have the funding available to numerically model more dams across the US to improve community safety. So I now will come back to the big picture research questions to answer them as best as I can. So for variable surface roughness, I will be investigating this fall in 2020. So I'd say check back in, likely in the upcoming spring. To accurately model the initial dam failure, phase 1 did demonstrate good agreement for downstream representation. We hypothesized that improved initial dam failure modeling, such as a gradual failure, will improve the model. And that remains to be seen, but that is our hypothesis. We incorporated historical data through the red outline and the historical boundary and the polygon, and also with numerical gauges. And so far I've used geophysics and applied mathematics for this dam simulation and for verifying this research problem. However, I'm looking forward to integrating more geosciences this fall. And another often overlooked but important part of research is outreach. So I'd like to walk you through 3 ways I'm working on community resiliency through outreach. So first, Dr. Brittany Brand and I worked to organize the Brent Carter Talk. Second, the BSU Geosciences Club, we organized a workshop. And third, I'm working on a short film. So I will dive slightly deeper into these. So first, the Brent Carter Talk was titled What Was Learned with the Teton Dam Failure. And this was set to occur after everything went into effect with the pandemic. So it's been postponed and hopefully it will happen virtually this fall. But the speaker was Brent Carter. He's a retired Columbia Pacific Northwest regional geologist. And this was a partnership with the Society of Mining, Metallurgy, and Exploration, or SME, the BSU HCRI, and also with the Bureau of Reclamation. And so I'd like to thank Chris Haynes at the Bureau of Reclamation for being my point of contact. The second outreach opportunity that was organized is the BSU Teton Dam workshop, which also has been postponed, unfortunately. And this focused on having Bureau of Reclamation and dam failure engineers and modelers on site at the Teton Dam failure. And we would get a tour and get to learn more about what happened there. And this would have engineering and geosciences components. And so this is a combination of a focus on higher education and also on building community partnerships between the Bureau of Reclamation and Boise State University. And finally, there is Modeling the Teton Dam, which is a short film. It's going to have 3 parts. The first part is available on YouTube at the link below, and it has closed captioning. And when I share it here, it doesn't have closed captioning. So I wanted that to be accessible so it could reach diverse populations. So you can access it at the link, or I can send it to Kendra to send out at the end of the talk. But this short outreach video is targeting high school students and their citizen science literacy so we can improve it, and also targeting citizens as a whole for why do we need to model the Teton Dam? Why do we need to model dam failures in general? And it's a partnership with the Museum of Rexburg, where they have museum docents who experienced the Teton Dam failure, and they would be able to give much more insight into what occurred that day, so it's not forgotten. As populations age, natural disasters are often forgotten, and we can't let that happen. So that's why I'm working on the short film. I would like to thank a couple people. So first, I would like to thank my research mentor, Dr. Donna Calhoun in Boise State Mathematics. I would like to thank Dr. Brittany Brand of the HCRI. I would like to thank Dr. David Wilkins in the BSU Geosciences Geomorphology section. I would like to thank Dr. Lejo Flores, who is in the Boise State Geosciences Hydrology section. I'd like to thank my late Papa Mike Spero. He worked for the USACE and also the Bureau of Reclamation for many years, but he was the first scientist I ever met, and we would go and dig up rocks and look at dirt together, and we'd go on hikes when I was younger. So I'd like to thank him for developing my natural curiosity for the world. And I'd also like to thank my parents, Michael and Melissa Spero, who are the #1 supporters in my life, and I wouldn't have been able to do this without them. I also would like to thank the HCRI and Boise State Research and Computing. I'd like to thank the Boise State Department of Mathematics and Geosciences for this collaboration with me as an interdisciplinary student. And I'd like to thank SME and the Bureau of Reclamation for their involvement in outreach and also for their support of this research. And I would like to thank one more time the IDAWRA and the ITC of NORFMA for this platform to share my research. I appreciate getting to connect with a larger audience and more people within the state of Idaho and this region. And here are some sources from my talk. And with that, I will now welcome questions. Thank you guys for your time.
Great, thank you, Hannah. Really nice presentation. Thanks for putting together all this. If you have questions, please type them into the chat box, and Hannah, I can read them to you, so you're not trying to read, process, and respond all at the same time. From Devin Stoker, great presentation, Hannah. What are your expectations for simulation runtime after increasing the topography resolution from 10 meters to 1 meter, and how would GeoClaw's adaptive mesh handle this?
That's a really good question. So I'll answer it in 2 different parts. So for my expectations of the runtime, I would expect it to potentially add between 15 to 30 minutes of extra computation time. So, and answering the second part as well, the adaptive mesh refinement focuses on only computing the gridding within the area that you're interested in. So although we might have high resolution topography for a large area around the dam failure with the drone photogrammetry campaign, we will be able to focus our sites specifically just on the reservoir in question and on the dam failure phase. And I use R2, which is the supercomputer at Boise State, so that speeds up simulations greatly. Without that, I would expect potentially, so it would take 24 hours if I ran it on my laptop originally, and that would take an extra 1 hour. So I'm very grateful to the research and computing, at Boise State for offering that resource.
Great. Thanks, Hannah. You mentioned 24 versus 25-hour run times, and I'm sure there are a number of us on the call who've done a lot worse than that on our laptop. So let's see. There's another question. Will B. Carter's talk be available through AWRA? I think we can certainly make that. Well, Hannah, is that something that we could make available?
Following this talk, I can reach out to Kendra and also through you, Mike. And I know right now the SME and the HCRI were co-hosting it, but I think the more people who see it, the better. So I definitely can put you guys in contact with them and we can move forward in that direction.
Yeah, at a minimum, if you could pass on the registration information for that talk, I think we could certainly distribute that as well.
Sounds good.
Another question from Devin. Manning's values are also based on depth of flow. Any thoughts on how your research might incorporate uncertainty? Also, any consideration to other flow resistance parameters other than Manning's roughness?
Devin, great questions today. So I'll answer that in two parts again. So the Manning values based on depth of flow and how that would incorporate into the uncertainty. I believe that was the question. So there is a significant amount of uncertainty in the model already. And the nice part about depth is this area is generally flat. If there was high sloping topography, our uncertainty would definitely increase. So with it being a general floodplain besides occasional buttes, and the depth gradually decreasing, I think we would definitely be able to integrate the Manning's value not only based on the roughness, but also on the depth. I think that would be a two-factor integration. I haven't read a lot about that, so I definitely could read more into it as well, just so I could understand it better with the depth of flow. And pertaining to your second part, Mike, correct me if I'm wrong, was it on flow resistance?
Yep, so any consideration to other flow resistance parameters other than Manning's roughness?
Yes. So with the Manning's roughness, we are planning to account for buildings that are in the areas such as Rexburg. Wilford was a really small farming town, so there weren't a lot of buildings. But in the larger urban areas, we are planning to account for buildings using the Manning's roughness. However, following the integration of the Manning's N, we can integrate bridges into the sequence or buildings or other infrastructure as well. So hopefully far down the road, we will be able to incorporate other flow resistance parameters.
Great. Hannah, I have a question on the adaptive meshing component. How refined will the mesh, how refined will the mesh, how far will the self-refinement of the mesh carry itself out? And did you ever get to any parts where you were you may be refining beyond the level of accuracy of the topography data?
That's a good question. I'm gonna find the image so I can share it. So as of right now, well, when I began working on this project, there was a model already in creation by Dr. Donna Calhoun. And so it did have the AMR instituted into it, but GeoClaw in general, it models to the topographic refinement. So if I'm inserting 10-meter resolutions, it'll model down to that, but it won't go further. If it's 20-meter, the grids will be a lot coarser and spaced further apart, but it will be accurate to the 20 meters. So here we can see how it's adaptively refining within the reservoir specifically and how it's being, like its computational efficiency isn't going to be affected even if we were to institute the 1 meter resolution. With the AMR, it is random, so it will compute at every time step. So we can go in and we can see if it's taking a lot of time to compute within the beginning time steps where we would have the 1 meter resolution. We can alter the time steps, so then it will be a coarser grid, but we can evaluate where the time is being spent for like the cost of the simulation. Let me know if that answered your question.
No, that makes sense. That's a good answer. So, and then my other question, I think, is probably related to Devin's as well. You know, how did did you do any Manning's roughness coefficient sensitivity? You know, beyond just doing a spatially. You know, I know you discussed using spatially varied, but did you vary that all to see how that impacts your either your wave attenuation or your flood depths?
That's a good question. I will be able to better answer it this fall. I'm planning on in August, September to do the Manning roughness structure for photogrammetry campaign, but I also can combine that with recent LiDAR surveys, and by recent within the last 10 years, but I can combine them with LiDAR surveys in the area to define which variable regions would require what Manning's coefficient would be necessary. I know other softwares like Anuga and HECRAS do already incorporate surface roughness, so I'm also planning on looking into those to see how they institute it. So I can hopefully have less errors initially, so it'll be a smoother process. But I am planning to look at flow depth also when instituting this roughness coefficient. I just, the project isn't quite there yet, although I'm quite excited about that part of the project.
Great, thank you. If there are any other questions, please type them into the chat window at this time. I don't see any that we're missing. Give people another minute to type their questions in. Okay, well, I don't see any other questions coming through. Hannah, thanks again for sharing your work with us, and congratulations on the recent award at the ASFPM conference. And sounds like you'll be continuing your research, so maybe we can schedule an update after the next round of simulations and the next round so we can continue the discussion.
Sounds good. I will keep the IDAWRA and the Idaho Technical Committee in the loop on where I'm at in my research.
Fantastic. Thanks again. And thanks to everyone for joining the webinar today. If you have, Hannah, is your contact information available if people have any questions to follow up?
Yes. I'll pull up my final slide quick. But my email is just my Boise State email, which is, if this wants to cooperate, but it's Hannah, H-A-N-N-A-H, Spero @u.boisestate.edu. And so that's right here in the bottom left-hand or right-hand corner for everyone. And then I also have a science Twitter where I post updates on like my numerical simulations and different geology things if you have a science Twitter.
Excellent. Again, thank you, Hannah. Thanks everyone for calling in, and we'll look forward to getting together on the next webinar. Have a great day.
Sounds good. Thank you guys for coming.